Okay, good afternoon. Happy Friday. Welcome to the third lab. Today we will first talk about the concept of spectrum. It's something related to Fourier transform, and it gives us a more general understanding of signals in the frequency domain. And then we will delve into transmitter design and see how we step-by-step construct a very simple transmitter. And then, of course, today's lab deals with the transmitter design as well, and you will see how you can transmit music wirelessly and then receive it on an FM radio and listen to it. Okay, so we're going to start with the concept of spectrum and understand what that means. Well, what we learned earlier was that signals can be examined in time domain or frequency domain. And we saw some examples of that. So we said I may have a signal like this, a sine in the time domain. And in the frequency domain, it has only two impulses at these two frequencies. So that was the view of the signal in the frequency domain. We said the energy is all concentrated at this frequency and this frequency. The signal doesn't have energy anywhere else, right? We saw that, for example, for a square wave in your homework. If you look at it like this, then the spectrum looks like that. You have a DC, and then you have some impulses here and some impulses here, and so on. We also noticed that the Fourier transform of a periodic signal can contain only impulses and nothing else. So that's what we learned before. So this is fine. But then if we have a random signal, for example, our voice, then the question is, can these concepts be still applied? In other words, can I still take the Fourier transform of the signal to obtain the frequency domain view of its contents? So the question is, if you have a random signal, and by that we mean a signal whose next value in the time domain may not be easy to predict, right? So it could be going up and down, and if I'm here, I don't know what the next value will be exactly. That's what we call a random signal. For example, if you speak into a microphone, and you examine the output waveform, it will look like this. And what we would like to do is understand how we go from here to some frequency domain representation. So what exactly should we plot here? You may say, well, why don't we just take the Fourier transform of this waveform, and whatever we get, we'll put it here. Well, it turns out that for a random signal, it is really not easy or even possible to define a Fourier transform. Okay? So we state that without proof. We say that Fourier transform is difficult to apply directly to random signals. All right. So then, in communications and signal processing, you might have encountered another quantity which has to do with the frequency domain behavior, and that is called power spectral density, PSD, also known as spectrum. So, in communications, we define the spectrum of a signal as the Fourier transform, but not the Fourier transform of the signal, but instead the Fourier transform of the autocorrelation of the signal. So it's a little different. What it said is, we won't take this signal x of t and try to find this Fourier transform. But instead, first we have to find the autocorrelation of this, and then we have to take a Fourier transform of that. And now you may not remember what autocorrelation meant and what this all leads us to, etc. But fortunately, there's a more intuitive approach of obtaining the spectrum. Okay? So we will have an alternative definition. Instead of calling it the Fourier transform of the autocorrelation of the signal, we have another definition. So alternative definition. Of spectrum. So the spectrum of a signal, at a frequency f1 is equal to, or is defined as, the power carried by the signal in a 1 Hertz bandwidth centered at f1. Okay? So think about this for a second, and I'll show you exactly what that means. It turns out that these two definitions are really the same thing, but the second one is much more intuitive and relevant to what we do in this class. All right, so let's try to see, if I show you how this is measured, then you will understand what it means. All right, so here's how it goes. I have a microphone, and I'm speaking to the microphone, so in the time domain, I have a random signal coming out, some voltage. Right? Well, I would like to find the spectrum of the signal, the spectrum of my voice. I know that my voice has components maybe from a few tens of hertz to maybe a few kilohertz, right? Audio signals can extend all the way to 20 kilohertz, but that depends on whether you're a man or a woman, you're young or old, and all these things. So, but typically around kilohertz we have some components. So what I'm hoping to achieve is the spectrum of the signal. In other words, I'm thinking that if I make a plot as a function of f, then I should have some plot like this, right? Starting from 0. So my question is, how do I construct this plot and what it means? Well, I will say, let's pick one frequency, f1. f1 could be, let's say, 1 kilohertz, right? So let's pick 1 kilohertz and ask how I would find the spectrum of my voice at a frequency of 1 kilohertz. In other words, how do I find this value here? All right, so this is f1 equal 1 kilohertz. So this is the measurement technique. I will take the signal, which could occupy a whole bandwidth, right? 20 kilohertz. And I pass it through a band pass filter. Band pass filter. That has this frequency response. It has a bandwidth of 1 hertz. And it is centered at f1. So what this means is that I will eliminate all the energy outside this frequency band, right? All the frequency components below 1 kilohertz and above 1 kilohertz are gone by this filter. This filter has only 1 hertz bandwidth, so plus 0.5 here, plus 0.5 here, conceptually speaking. So I let the energy in this vicinity go through, and I reject everything else outside. Now, I take this to a power meter. Okay, so that's the power meter. Again, this is a conceptual measurement. And this power meter will give you a number, right? And that number, that average power, goes right here. That's what we said. The spectrum of a signal at frequency f1 is equal to the power that the signal carries in a 1 hertz bandwidth centered at f1. And this, from now on, will be called S of f, spectrum of f. Spectrum as a function of f. Okay, now if I want to measure how much power my voice carries at 2 kilohertz, what do I do? Well, it's the same measurement, right? Except that this time I have another bandpass filter, and this bandpass filter this time has a center frequency of some other value, 2 kilohertz maybe. Still 1 hertz band. So again, it goes to the power meter. I measure the output power, and I find another point. So that point is right here, and that is F2. And I can see how it goes. So in principle, you have a whole bunch of bandpass filters centered at 20 hertz, 30 hertz, 40 hertz, 100 hertz, 100 hertz, 1 kilohertz, 2 kilohertz, etc. Right? And your signal is driving all of these bandpass filters, and you're measuring the output powers of all of these, and you're finding these points and putting them here. And the result is what we call the spectrum. So if we perform this test for a woman's voice versus a man's voice, this is what we should observe, right? So a man's voice has lower frequency components. That's a man's voice. And a woman's voice has high frequency components. So that's a woman's voice. Okay, so for example, a man's voice may cut off around 5 kilohertz, whereas a woman's voice may cut off around 10 kilohertz. And by cut off, I mean it becomes negligible past that point. All right. A children's voice might actually extend all the way to 20 kilohertz. All right, so that's what we call the spectrum of a signal. For any signal, you can do that. In fact, whether the signal is periodic or random doesn't matter, because this test is more general than the simple Fourier transform that we defined before. Even if you give a sinusoid in this test, you will get the same result as before, right? Because you give a sinusoid at some frequency, let's say 1 kilohertz, right? Or let's say 5 kilohertz. You place this bandpass filter at a center of 1 kilohertz, right here. So do I have energy? No, this guy has no energy at 1 kilohertz. But at 2 kilohertz, do I have energy? No, no energy, so nothing. Up to 5 kilohertz. When this bandpass filter is centered at 5 kilohertz, suddenly we get a lot of energy. We measure some power, and that power is this value or that value. All right, so for periodic signals, the concept of spectrum is also applicable. So that's the more general definition of what we should expect to see in the frequency domain than the simple Fourier transform that we defined before. But in any case, we can use that one for anything we want. Any questions so far on the spectrum? Okay, so some examples of spectrum. So for a high-quality audio signal, if you have a high-quality music player and all that, and you find the spectrum, what you should see is it starts from about 20 kilohertz, 20 hertz, sorry, and goes to about 20 kilohertz. So it has some behavior like this. Okay, that's where most of the energy resides. Below this, it has very little energy, and above this, it has very little energy. So that's for audio signal. So today, when you connect the music on your laptop to the signal hound, which does this, you should see something similar to this. Now, it may not extend to 20 kilohertz because your laptop player may have a low quality, so it cuts off things beyond 10 kilohertz or something. Okay? But in principle, that's what we need. All right, how about a video signal? A video signal is a signal that is coming when you're playing some video or movie or something, right? So that's not a signal. For example, if you have a TV and it's playing a video, and you go and monitor the signal that's going to the pixels, that signal as a function of time has some variation. It's a random signal. And now if you perform this measurement on it and construct the spectrum, what you will see is that it extends to about 5 megahertz. And this is not HD, okay, not high definition. For high definition, it's about 20 megahertz. So that's the spectrum that you would observe for a video signal. Now, these spectra also tell us what we need in terms of circuit performance if we are processing audio signals or video signals. If you're building a good audio amplifier, obviously its bandwidth has to be at least 20 kilohertz, right? So It has to be flat. The frequency response, the gain has to be flat up to 20 kilohertz. In the case of a video amplifier, the frequency response, the gain has to be flat at least up to 5 megahertz. All right, so that also tells us about the circuit requirements. Okay, good. These are some simple examples of spectrum. Any questions? All right. Now, a couple of notes. Number one, do we really need this many filters here? That seems rather complicated, right? So how do we do this exactly? If I want to measure from close to 0 to 5 megahertz, here, right? You need this many bandpass filters. So that would be impractical. That's not something we can do. So in reality, you can have maybe one filter, and this bandpass filter can be programmed. You can go up and down the frequency. Imagine there's some sort of capacitor somewhere, and you switch more capacitance or less capacitance, so you move the center frequency up and down. Or there are other techniques. So in reality, we don't use this many filters. The second point is that what you see here, this measurement is exactly done, the conceptual measurement, by a spectrum analyzer. So a spectrum analyzer, which in our lab is embodied in what we call the signal count, right, the box, measures the spectrum. Previously, I didn't really call this spectrum, we just called the Fourier transform, because we were looking only at sinusoids and periodic signals, right? So it was fine. We had only impulses in our observations. But today, when you look at, for example, music, then it's no longer an impulse. It has some form to it. And then that's what the spectrum analyzer does. Yes?
So you're saying it does it through bandpass filters, but I thought a lot of these spectrum analyzers did it by using an FFT.
Right. Well, the conceptual idea is a bandpass filter. Now, the bandpass filter is an analog domain or digital domain. It doesn't make any difference.
Okay, so that's the analog.
Right. So we can add FFT as a bunch of bandpass filters in the digital domain, as opposed to analog. But when you define the spectrum, you can't say spectrum means take the FFT. Because then what's the definition of FFT? I have to go back to the Fourier transform. Well, it's not a Fourier transform of the signal itself, it's the Fourier transform of the autocorrelation of the signal. Okay, so we have to be careful about that.
So you're saying they're not the same?
Which one?
FFT and spectrum?
The FFT, okay, so if you take this microphone signal and take the FFT of it, that's not the spectrum. What happens is, if you're curious, what happens is that if you keep taking the FFT of a signal directly, regardless of how long that FFT is, the spectrum does not converge, meaning the spectrum does not approach its final value. If you take the FFT of this random signal, this is what you will see. So as a function of frequency, you'll see something like jumps up and down. It has huge amount of noise on it. And regardless of how long you make this, and you take the FFT for longer and longer, this does not converge. This deviation doesn't go away. But what you can do is you take one FFT of this guy, you take another FFT, and then they average the FFTs. And then that brings you to a smooth spectrum. Okay? So that's the distinction between taking the FFT or Fourier transform of the signal directly, or taking the Fourier transform of the autocorrelation of the signal. All right? But for us, it's easier to look at it this way than through autocorrelation, even though they are equivalent. Okay, any other questions? Okay, so that's all I have to say in regards to Fourier transform. Spectrum. A couple of things that we know from Fourier transform days also are applicable here. So remember that we said multiplication in time domain was equivalent to convolution in frequency domain, right? So that applies to spectra as well. The other thing that we knew was convolution with an impulse simply shifts the spectrum up or down, or to the right or to the left. So that applies to Fourier transforms and to spectra as well. The right and or the left. Okay, so that's also something to remember. In your homework, you play with this, homework number 2, and so on, but that's what we need to know. Okay. Spectrum has many applications, not just in electrical engineering, signal processing. When you want to observe, for example, a star or a galaxy, the only thing that you have available to you is the light that's coming, and you look at the spectrum of the light, right? And by looking at the spectrum of the light, you can determine a lot of things. For example, you know that if an object is going away from you because of Doppler shift, its color is shifting to higher frequency, shorter wavelength. It's coming towards you. If it's going away from you, it shifts towards red. If it's coming towards you, it shifts towards blue, or vice versa. I don't remember. But from the spectrum, these are the things that we can discover. For example, that's how they discovered that the universe is expanding, right? Because the ones that are farther are going faster away from us. Anyway, okay. Now we are ready to look at transmitter design. And if you remember, we said that we have a microphone that generates a signal in the time domain. And this goes to our transmitter. The transmitter drives an antenna, and we generate an electromagnetic signal that propagates through the air and is eventually picked up by a receiver. So that's good. And what we would like to do today is understand what goes on in here. All right. So, Log, can I give you a piece of wire? So the way we will approach this transmitter design is by making 2 observations. All right, thank you. That's too long. Give me something shorter. Okay. All right, thanks. So the way we approach this transmitter design is by making 2 observations. So observation number 1. All right, so here's a piece of wire, and I will form it into a little loop, like so. Okay? So what electric device does this remind you of? From EE10, 110 kind of thing? Kind of inductor, right? Looks like an inductor. It's 1 turn. Inductor usually has more turns, right? Okay, so this loop looks like an inductor. So let's write that here. I have a loop, and I'm thinking that maybe this is an inductor. And an inductor is denoted by this symbol. And an ideal inductor is a component that stores energy, right? If it carries a current of I, its energy is 1/2 Li squared. It does not consume or dissipate that energy. You give it that energy, you can take it back later. Like a capacitor, you give it energy, you can take the energy back, right? The energy doesn't disappear, it doesn't go anywhere. Okay, so that's good. This is an inductor. This inductor can store energy. If you give it a voltage source, maybe an AC or DC or something, and this voltage source produces some signal, this can store that energy in some form and take it away from the signal source or give it back to the signal source. All right, so far so good. But then you have also seen structures like this on the rooftops, on the top of vans and things, used as an antenna, right? Something similar, maybe squarish, maybe rectangular, and so on. So we suspect that this might also operate as an antenna. And the question is, what is the electrical model of an antenna? The capacitor, inductor, resistor, transistor, what? How do you model an antenna? A good antenna, a perfect antenna. Well, in a perfect antenna, if you apply voltage to it, you give it energy, what does that antenna supposed to do? What is it supposed to do with that energy? It's supposed to radiate. It's supposed to go away. So every piece of energy that you give, every joule of energy that you give to the antenna, every joule of energy that this guy gives to the antenna disappears. It's not stored here. It doesn't come back. It's not retrievable anymore. So as far as this voltage source is concerned, the antenna looks like a resistor. Because you gave it energy, then it disappeared. So a good antenna is modeled by a resistor. Okay? And that makes sense. If you really had a physical resistor, and you applied a voltage to it, what would happen? The resistor would heat up. The heat comes out in the form of infrared. Infrared is an electromagnetic signal, except that it has a very long wavelength, right? Well, not as long as our 1 gigahertz waveforms. Now, if you give a 1 gigahertz waveform to this antenna, and it dissipates it, it radiates it, it still radiates in an electromagnetic form, except that it's not infrared, it's some lower frequency, 1 gigahertz or something, right? So an antenna, a good antenna is a resistor. A good inductor stores energy. So then the question is, how does this structure decide whether to behave as an inductor or a resistor, or a mini antenna, right? Under what conditions does this loop decide to store energy and not dissipate any, or radiate it completely and store none? Okay, so that's the question. Does anyone know the answer? So we have the same loop, and it can have two different roles, two very different roles. Well, the way this loop decides is based on the wavelength of this signal. Okay? This signal is an AC signal, it's a sinusoidal signal, a certain frequency, therefore a certain wavelength. Based on the wavelength of that signal, this loop decides what to do. So here's the observation. If the dimensions of a loop are comparable with a fraction of the wavelength, then the loop radiates. Okay? Meaning it does not store energy. Okay, so that's the key concept in antenna design and in general in how you look at a circuit component and decide whether that can be a nice little inductor or it can be something more complex like an antenna. All right? Okay, but this observation actually dictates the design of a transmitter in a slightly different way. So what I said was, to build a good antenna, I have to pick the dimensions of the antenna, like diameter or something, right, to be comparable to the wavelength or fractional wavelength, maybe lambda over 4, lambda over 2 or something. All right, okay. So let's try this then. First, attempt to build ATX. Why don't I take my microphone and maybe amplify the signal. The microphone signal is not that large, right? Just a simple amp, audio amplifier, and then directly give it to an antenna. Voila. That should work, right? Okay. Well, sure. The only thing is, how much is the wavelength of the signal that's coming here? Well, at 20 kilohertz, which is the highest audio frequency, by the way,